Okay, so that is nice. It turns out that it's relatively easy to understand what we had observed empirically. But now the question, or now one question that we can ask is, well, how do we stabilize this system? So one thing we could do is, and there are obviously a lot of things that we can do, and eventually we'll introduce a lot more theory that will allow us to perhaps do this in more systematic ways. But one thing that we could do is actually choose a controller that makes System 1 kind of look more like the controlled version of System 2. So that is, if we choose a controller that basically replaces this numerator with this numerator, then I'm actually going to get a system that should have the same poles. So in other words, I get the same 1 plus pk equals 0 equation for System 1 if I choose a controller that looks like this. And again, this is not necessarily the smartest thing to do, but what we can do without knowing anything else or developing any other theory is we can use the fact that we know that our controller works for a similar system, or use the fact that we know that a k equals 1 proportional controller works for a similar system to find what can be thought of as an equivalent controller to stabilize our System 1, which proved to be a little bit trickier to control. So in practice, what I can do now is define a new controller for our System 1, where, again, I'm putting my open loop system in feedback with a k, but now my k is a transfer function. So it's not a proper transfer function because the degree of the numerator is greater than the degree of the denominator, but that's okay. And so what I can do is run this. I can look at what I get. And at the end of the day, if I look at my transfer function between my new controlled System 1 and the controlled System 2 with k equals 1, down the bottom here, I see that they have the same denominators. So the numerators are still different, but at least I've managed to put my poles sort of where I want them, or where they'll be stable. And there's sort of a technicality here in terms of basically to do this feedback, I had to go to transfer function notation because Python doesn't like non-proper systems in state space form, and then I had to adjust my state because it kind of changed. But that's a minor technicality, but at the end of the day, when I simulate this system, I now have a stable response for both of my systems. So that's nice. So again, I'm turning on control at a particular point. The orange curve is the original System 2, which was stabilized with k equals 1, and then the green curve is that controller that I designed to try to get a system that looked kind of like System 2 when it was controlled. They're different, though, again, because the numerator of the transfer function is different. Are there any questions so far? Okay, good. So we're going to do things a bit more systematically now. But I'll mention that really what we've started to do is look at some special cases of PID control. So that is where we have a controller with relatively simple dynamics that includes a proportional term, a derivative term, and those two are what we have here. And then we can also have an integral term. And so intuitively what's going on here is that we're taking our output and then we're saying that our control input, or the input to our system, is going to be a function both of that output and then also its integral and or derivative with time. Or in other words, if let's say our output was sinusoidal, say, then we're really sort of shifting in phase to get the derivative and the integral terms. And there are many ways and rules of thumb that one can use to tune these parameters. This type of control is still used a lot in industrial applications, for example. It's relatively simple. If you know what you're doing, it can work relatively well. Sorry, that should be a D, not a P, I realized. But it still requires potentially some sort of guessing or sort of twisting of knobs to obtain some desired behavior. And so and again, I could go back to the notebook and start playing around with these things, but in the interest of time, we'll keep pushing through. But feel free to play around with that yourselves. Okay, but more generally, if I have, say, a simple controller, I might want to be able to predict something about the performance or the stability characteristics of my closed loop system. Now, in the example that I showed, it was actually relatively simple to, from first principles, determine where my closed loop poles were. But that really relied on me only having a two-dimensional system which had a quadratic that I needed to solve for the poles, and I could use my quadratic formula, and so everything works out nicely. More generally, though, if we had a higher order system, so that is if the denominator of our transfer function was a higher order polynomial, then it quickly becomes intractable to solve. And so that motivates sort of the design of tools that can help us make these predictions without having to do the precise math. And so that motivates the root locus plot. And so what this is it's a plot of all of the poles, all of the closed loop poles that you get that are parameterized by some constant within some controller. So most simply, this could just be proportional control and looking at all non-negative constants of proportionality. Or more generally, if you can take a factor of k out of your controller, so that is, let your plant multiplied by your controller be equal to k multiplied by some other transfer function, then you can do things that way as well. And so it will turn out that it's actually possible to look at what these root locus plots look like, say in Python or MATLAB, but also it's possible to predict what they look like using a few simple rules just by hand, which is, I guess, good if you're ever stuck without a computer and need to stabilize an unstable system or something like this. But also it's good to understand why a root locus plot looks like what it does. So that's what we're going to look at now. And this, I think, will make more sense when we go through an example. So once again, it's sort of a one-liner in Python or MATLAB. We have an inbuilt rlocus command. And it will either output the plot itself automatically if you have plot equals true. I think in Python in particular, it's kind of nice to do things a little bit more manually, so at the expense of having more lines of code. But basically what I'm showing here are the root locus plots for proportional control for my two systems. So again, these are systems with the same A matrix, but different B and C matrix pairs. And so we see for system one, remember this is the system that we weren't able to control, or that was still unstable when we used our simple k equals 1 proportional feedback. We see that the eigenvalues or the eigenvalues are along these blue lines, which we observe never cross into the left half plane. So that's consistent. Conversely, sorry, this should be system 2, not system 1, but I can change that. We see here that as our controller gain changes, our poles, which originally were at these red crosses, move towards the left half plane. Again, consistent with what we had found empirically. Okay. So now the question is, do we understand or can we predict why these plots look like this? And that's what I'm going to do next. So it turns out that root locus plots can be constructed or approximated using a few simple rules. So to start with, root locus always starts at the open loop poles, or the poles of G of S, which in our case for proportional control is just the open loop poles of our system. So that is why these scales are different, but we start, or one end of our root locus, which corresponds to k equals 0, is at these open loop poles. Secondly, a point on the real axis is included in the root locus if there's an odd total number of poles and zeros to the right of it. And here's where the fact that our system 2 has a 0, but our system 1 does not, starts to have an impact. Because the total number of poles and zeros for our system 2 is 3, which is odd. So what that means is that everywhere to the left of, well, to the left of all three of these guys is going to be included in the root locus. So that means there is a k value such that any point on this blue-colored portion of the real axis is an eigenvalue for our system. And actually, it goes all the way up to where this 0 is, because, well, these two poles are both at the same location, so every point to the left of this 0 has either 1 or 3 total poles and zeros to the right of it. So it doesn't particularly matter whether this 0 is to the left or the right of these poles. And then lastly, as our controller gain goes to infinity, the branches of the root locus, which go to infinity, asymptote to straight lines that are given, whose angle with the positive real axis is going to be given by this. And it turns out that the number of these lines that go to infinity is given by the relative degree, which is the number of poles minus the number of zeros of our transfer function. So again, the relative degree of system 1 is 2, because we have 2 poles and no zeros, while the relative degree of system 2 is 1, because we have 2 poles and 1 zero. So that means that system 1 has 2 lines going to infinity, and if we use this equation, we find that those lines are at pi on 2 and 3 pi on 2, whereas here we only have 1 line, which we find is at negative pi, which is consistent with our finding regarding the real axis, or this rule 2. So the point that I'm making here is that even if we didn't go through the math explicitly, by sort of using these rules, we could infer that proportional control is never going to stabilize, or proportional control, is never going to stabilize system 1, but is able to stabilize system 2. And there are more complex rules that can help you out, which can be particularly important if you have more complex systems with lots of poles and zeros that might be close to each other and so forth. Okay, so I wanted to introduce, this is sort of one method to study the dynamics of linear systems, or particularly the response under control. It's one of several methods. I'll mention a few more later on. We're not going to have time to cover all of them because, again, this is sort of an abbreviated course in controls. But the idea here is that we can use these tools to build up or validate our intuition or our empirical findings regarding what works and what doesn't. Okay. So now we're going to change pace a little bit. So rather than taking just our output y as the input to our controller, we can also have cases where we actually have access to the full state, or perhaps an estimate of the full state. And I'll talk a little bit more about that later on. So that changes the topology of our control diagram a little bit, but more or less it's the same. It's just that we have a vector now going directly out of this state propagation equation through our controller and then to define our control law and thus our input to this system. And then our output block can be considered separately. And in this case, as before, we have modified closed loop dynamics. The only difference is that we don't have a C term here now because K acts directly on X. So why am I introducing this? Well, I guess it should, in theory, allow us to do better because we know the full state rather than just the output, which might be, in this case, and is in this case, a limited number of states. But it also allows us to develop other tools. So for example, we could ask, well, maybe we're going about this the wrong way. Rather than designing a controller and then seeing what it does, or maybe using some tools to design a controller but then needing to test it anyway, could we start the other way around and ask, can we explicitly say, I want to have closed loop poles at these particular locations? Maybe because that will stabilize our system. Maybe it also has other favorable dynamics in terms of how quickly we'll drive our system to zero. And use that explicitly to design a controller. And the answer is yes, provided that our system is what we call controllable, which means that we're sort of, through our control law, able to drive the system to whatever state we desire. But that controllability can be tested through looking at the rank of the controllability matrix, which is what you get if you stack together your input matrix, or vector B, with successive powers of A. And so it turns out that computing the rank of this matrix will determine whether your system is controllable. Which means, at the end of the day, one, as I said before, it means you can drive the system to whatever state you want, but also you can design a controller that will put poles wherever you want them. And so I won't say too much about the theory as to why this is the case, but we can see for our simple system in practice whether or not we can do this. Okay, so now we're on to looking at full state feedback. And as I said before, our first step is to verify that our system is controllable. So once again, I don't have to form the controllability matrix by hand. There's a nice shortcut, which is exactly the same as what's in MATLAB. And then I can just compute the rank of that. And my system has two states. The rank of my controllability matrix is 2, so we're good. And this is system 2. This is system 1. I could also look at system 2. And it turns out that's also controllable. And again, I only need the A and the B matrices to compute this. So I claimed that means that I should be able to put poles wherever I want them. So we can try this. And so this is called pole placement, which is one form of full state feedback that we can implement. So how do we do this? Well, I start off saying I want my closed loop poles to be, in this case, at -1 and -2. So in the left half plane, so I have a stable system. I can design my full state feedback law, which now is going to be a matrix that maps between my system state and my input. So it's going to be a 1/2 matrix. And then, so I can do this. I get my controller gains. So this is what I multiply each of my state components with to form my input. And then I can verify, when I look at the closed loop poles, that they're exactly where I asked them to be. So this is nice. We now have full authority to put poles wherever we want. So if I wanted one of these to be at -10 rather than -1, then my controller gains increase, but I can get the desired closed loop performance. Are there any questions at this point? Okay. But this still seems sort of arbitrary. Like, it's nice that we can do this, but we're kind of relying upon some sort of intuition or knowledge of what we want our closed loop dynamics to be to decide where we want to put our poles. So that sort of motivates the question, can we define a controller that is in some sense optimal? So what might we mean by optimal? Well, perhaps we want a controller that's very good at making the output of our system whatever we want it to be. So that is tracking a desired reference signal, which what we've looked at so far just means driving our output to 0. Well, at the same time, not wanting to exert too much energy. Or mathematically, we have a cost function where we sort of have a penalty on non-zero states of our system and a penalty on how much energy our controller needs to exert. And so some of these methods actually are sort of a simplified or special cases of some of the ideas that Professor Schmidt was talking about last lecture, where we have an optimization problem that we wish to solve, which for linear systems is relatively easy to do.